Welcome. This is the beginning of my physics show, but before we begin, I'd like to give a few notes first. The reason why I'm making this is to help students at school not well understanding the basic concepts of electricity. Also, I'd like to give some thanks to my friend Emily, who basically convinced me that I'm able to explain these phenomenons in physics well. It was at a time when I explained to her about amplitude-modulated radio and frequency-modulated radio. Also, I'd like to give a shout-out for George Yu, who asked for one nicely. He's also my third or fourth subscriber. In this episode, we're going to figure out what electricity is and study Ohm's law. This is to study the basics of electricity you may have forgotten over the years and build up a little on it. We live in a world full of electricity. It gives us light and several different utilities that are seen as indispensable today. Technology is advancing faster and faster today, so it's essential that you at least have a basic understanding of electricity. But what is electricity? To understand that, we will have to size down to the atomic level. What you're looking at resembles an atom. It is not to scale, for the proportions of the subatomic particles would be impossible to show on your screen. All matter is made up of atoms, and all atoms are made up of subatomic particles. Atoms have a dense nucleus made up of positively charged particles, called protons, and particles with no charge, called neutrons. Around the atom, orbiting at inconceivable speeds, are negatively charged particles that are nearly weightless, called electrons. Let's slow this down so we can get a better look at them. An atom has no net charge on it when it has the same amount of electrons as protons. However, this balance may be disturbed, and the atom would have an electric charge on it. A charged atom, or molecule, is called an ion. Charges may only be obtained when the amount of electrons in an atom or molecule changes. The number of protons never changes. If an atom or molecule has an excess amount of electrons, then it is a negatively charged ion, which is called an anion. If an atom or molecule is missing electrons, then it is a positively charged ion, which is called a cation. Whenever a difference of electrical charges is made, there's a force that tries to bring the net charge back to neutral. This is the electromotive force, or EMF. Since this is a type of energy that can do work, it is potential energy. The difference in charges has its own unit, called the volt. If there is a high potential difference, then there is a greater force between the two charges. Here's a capacitor that can charge to a high potential difference using static electricity. For example, with this comb and my hair. I've actually made this capacitor like a year and a half ago during the summer. This may take a while. Here's a capacitor charged with a high potential difference. Notice how that arc jumps across the two conductors. Here we have a capacitor charged with a low potential difference. Note that the two conductors have to nearly touch each other in order to do work. In order for electricity to flow from one charge to another, there must be a good path for it to flow through. That is, there must be a conductor. Think of it as a water slide. There are children at the top of the water slide with potential energy. When they go on the water slide, they'll use their potential energy into kinetic energy, and then they'll arrive at the bottom with no energy left. And then they'll take their designated path towards the stairs of the water slide, go back up, and then the same cycle repeats again. They get potential energy once more. So, alright, so copper, for example, they're good conductors of electricity. However, glass, on the other hand, is terrible. It's a bad conductor of electricity, and it's often used to insulate. barriers to prevent current from flowing. Aluminum, it's still a pretty good conductor of electricity. It's just slightly inferior to copper in conductance. An example of which glass is used as an electrical insulator would be in power lines. Let me draw it out for you. In this transmission line shown right here, you can see that there are two wires that the transmission line is holding. On the points right here and right here, you can see that they're being held by these things, which are typically made of glass or ceramic. It's to insulate the wires from this metal cage or body that the wires are being carried by. Also, these wires are typically about 200,000 volts, so it's pretty essential to keep them far apart from each other. An example of which copper and aluminum are used as electrical conductors are in electrical wiring in houses. However, since copper is a better conductor than aluminum, that means that you'd rather have a house that's wired with a copper wire rather than aluminum wire. Also, aluminum is a terrible conductor for contacting between terminals. All conductors, whether it's aluminum or glass or water or whatever it is, they all have their own amount of resistance. The unit for resistance is the ohm, using the Greek letter omega. The unit for electrical current is the ampere, often shortened as the amp. This is the rate of how many electrons pass through a conductor per given time. Now, in equations, you'd often see the ampere as a capital letter I. According to what's called Ohm's law, voltage, resistance, and current all relate to each other. The voltage is the product of the current times the resistance. An electrical conductor with a resistance of 1 ohm and a current of 1 ampere, the voltage is 1 volt. If you want to run 3 amperes through a conductor of 1 ohm, what would you do? Hopefully, you set to increase the voltage to 3 volts. The relationship between voltage and current is linear when the resistance remains the same. If you increase the voltage, the amount of current which can flow through the conductor increases proportionally. Here's a second scenario. You have a voltage of 10 volts with a current of 2 amperes running through a conductor with a resistance of 5 ohms. You suddenly decide that you want only half an ampere to flow through the conductor. What will you do? You may have said to decrease the voltage to 2.5 volts. You may also change the resistance to 20 ohms instead. Looking at the equation again, we can see that there is an inverse relationship with the resistance and current. If you double the resistance, then the amount of current flowing through the conductor halves. Triple the resistance, and the current cuts down to a third, etc. Whenever current is flowing through a conductor with a resistance, then a voltage is present across the conductor. A component designed to have a certain resistance is called a resistor. In this circuit, we have a voltage source, a resistor, and a couple of electrical conductors to connect them together. When a path for current to travel is given between a voltage, then the potential energy is used up and converted into a different form of energy. Most of the voltage is present across the resistor, as there is almost no voltage across the conductors. That means that about 6 volts is present across the resistor, and most of the energy will be used up there. The resistor will then end up heating up. Whenever current flows through a conductor with a resistance, and let's face it, all conductors have some certain amount of resistance in them, that means the electrons collide with the nuclei of the atoms, and when that happens, heat is produced. In a good conductor like copper, That means there's less collisions that goes on in the conductor. However, in a conductor like iron, which is still a fair conductor but not as good as copper, there's more collisions that go on and more heat is produced. That's why houses are built with copper wire, not iron wire, because it'll heat up too much when current flows through it. And that's what keeps our houses from burning. There's a case, though, which we use electrical resistance to our advantage, and that's the typical light bulb. A typical light bulb has a very thin tungsten wire that's coiled very tightly, and sometimes even double coiled. Whenever current flows through a wire with such a high resistance because it's so thin, a lot of heat's produced, and when it's coiled into a very tight size, a compact size, then all that heat is concentrated and will emit a lot of visible light. The unit for power is what? Was your answer the watt? Because if that's so, then you're incorrect. Listen closely to the question once more. The unit for power is what? Your answer should be yes, because the unit of power is watt. Now, the rate of which electrical energy is expended is called the watt, sometimes known as joules per second, but let's use the watt. Power may be measured using the product of the voltage and current. Looking at this light bulb, the voltage rating is 5.2 volts, and the current rating is 0.5 amperes. What is the power of this light bulb? Your answer should be 2.6 watts. Alright. Here's another problem to solve. I have this light bulb that operates at 60 watts at 120 volts. How much current would run through it? Your answer should be 0.5 amperes. Thanks for watching. I really appreciate the fact that you've taken your time to watch this video. Please leave a comment for how well I've done. Did I explain everything well? Or were there things for me to improve? My next video will be an audio presentation of my 300 seconds documentary called Kids These Days. This originally began in September, but due to the lack of people willing to act in the video, it has been discontinued. I hope you enjoyed my video. Tune in next week for the return of 300 seconds.